so today we're going to talk about 6.6, de Moivre's theorem and nth roots. Okay, so we're going to talk about de Moivre's theorem today. We won't talk about it today, but so we're going to introduce a new concept called the complex plane. In other words, we had a Cartesian plane before, right? Where we had the x's and the y's. So we're going to have a complex number, and we're going to call this the real axis, and this will be the imaginary axis. Imaginary axis. So the real portion of this number will be plotted on the x, what we would traditionally call the x-axis, and the imaginary we would plot it on the y-axis. So in other words, if I were to plot this, this would be z, and it would be a and b. In other words, this guy here would be a, and this guy here would be b. Okay? And so this is a complex plane. Okay? So this has some interesting characteristics, and the first one is on example number one. In example number one, it tells us to plot two of the complex numbers and then add them together. So we have u is equal to 1 plus 3i, 1 plus 3i, and then we have v is 2 minus I. V is equal to 2 minus I. So if I plot this, what do I get? I get u would be 1 and 3, so this would be u. V is 2 and negative 1, so 2 and negative 1. Well, if I add them together, what do I get? I get u plus v is equal to nothing more. We add the real together, and then we add the imaginary together, and we get that. So if I plot that, what do I get? I get 3, 2, right there, right? So this would be v, and this here would be u plus v, correct? Well, the interesting part is that if we were to consider this as a vector plane, right? If we remember the vectors, right? We did the same thing in the vectors, right? We added the x's together and we added the y's together. In other words, you're going to get the same concept of adding this vector and this vector is going to be equal to that vector. So you're basically doing not only doing the same operations, but it ends up being the same thing. Okay? So that's kind of interesting there. Okay, so let's flip the page and go to page 504. So what we're really going to talk about, and what's going to get us to de Moivre's theorem, is when you plot, or when you set the z, let's go back and set the z as a plus bi, okay, you can actually represent this in a polar form, okay? So you're going to call this is what? So this guy here is A. You have A here, and then you have B here, correct? But if you put this in a polar form, you can call this, we would call this R, and we would call this theta, right? So A is going to be equal to what? A right here is going to be equal to R cosine theta, whereas B is going to be equal to R sine theta, okay? In other words, you can represent this guy as R cosine theta plus I sine theta. Okay? So why do I put the I in front of here instead of behind here like this one over here? Well, we don't want to say sine theta I, right? So we want to put the I up front to make sure that, to just kind of signify that this is on its own here. Okay, so I had taken the R's out, pulled the R out, and I get cosine theta plus I sine theta, right? Okay, so this is actually written so often, okay, and then the only thing that's really important here is the R and the theta, right? It's the R and the theta, right? Because the other things are not going to change. You're always going to have a cosine, you're always going to have a sign. So this is actually abbreviated as RCIS theta. Okay? So mathematicians, in math, we actually can write this as RCIS theta. Right? And you'll see this quite often. All right? So, if you go to page 504, it shows a definition of the polar form, where R is called the modulus, or absolute value, or the modulus. Theta is called the argument. Okay? So we have the absolute value here, and then we have the argument. All right? So let's go ahead and see how this actually works. Okay? So let's go and see if we can do example 2 and present those two to turn them into polar form. So we have 1 minus root 3i. So I have 1 minus root 3i. So this would be my A, and this would be my B, right? So my R is going to be equal to what? R is going to be equal to square root of what? A squared plus B squared is R squared, right? So I'm going to get R is going to be 1 squared is 1, and then this squared is 3, right? So I'm going to get that. And then, which is going to be what? This is going to be 4, so it's going to be root 4, so it's going to be 2, right? So this is the same as basically 2 1/2 minus root 3 2i, right? You see where the 2 came from. So basically, because I pulled the 2 out, I'm going to get this guy and this guy, right? Okay. Theta, actually, I guess I haven't written this down. Theta is going to be equal to what? Theta is shown as tan B over A. So theta is tan theta, or tan theta is B over A, correct? B over A. Okay. So what is B over A here? What is B over A? I have B negative 3 over A. So I'm going to get, this is going to be tan theta is root 3 over, negative root 3 over 1. So I'm going to get negative root 3. Okay, so when is tangent going to be that? In other words, when is the cosine going to be this? And when is the sine going to be this? So you have to go back to thinking our unit circle. So my sine is positive, cosine is negative. So where does that happen? That happens in the second quadrant. So I'm in the second quadrant, right? Second quadrant where the sine was 1/2. So I'm in the second quadrant over here where the sine was 1/2 like that, right? 1/2 right there, okay? So what is it? I'm going to get 5 pi over 6. It looks like 5 pi over 6. So this is going to be equal to 2 cosine 5 pi over 6 plus I sine 5 pi over 6. In other words, the same as 2 CIS, right? 2 CIS 5 pi over 6. Okay? It says 5 pi over 3. Why am I at 5 pi over 3? Cosine, okay. This is cosine, so cosine is positive. Okay, let's go back. All right, so we had here, okay, we got to here, tan negative root 3 over 1 was negative root 3. So this is the cosine part, right? This is the cosine, so I was wrong here. Cosine is positive and sine is negative, which means that we're in the third quadrant. So we're in the third quadrant where cosine is negative 1/2. So we're going to be over here, right? We're going to write over here. So cosine is positive, sine is negative, third quadrant. So we're going to go over here. So that's going to be 5 pi over 3. So we're going to get 2 CIS 5 pi over 3. So that's going to be your answer. Okay? Let's see if we can do so if we can do the second one, B. I have -3, -4. What? Oh, okay. I'm wrong again. Cosine is positive, sine is negative, so we're actually in the fourth quadrant. Fourth quadrant here, where cosine is 1/2, so it's right over here. So yes, we are in 5 pi over 3, but we're in the fourth quadrant. 2 CIS, 5 pi over 3. Okay? So let's go ahead and do the second one. Was -3 minus 4i. So my r is going to be what? What is my r going to be here? So I'm going to get r squared is equal to 3 squared plus that squared. So r is going to be the square root of that, which is 5. So this is going to be equal to -3 over 5, -4 over 5i. Okay? Negative, negative, so I'm in the third quadrant. So I'm in the third quadrant, somewhere down here. Like that. So you're going to find this value. So you're going to find the what? Tangent is equal to what? Tangent theta is equal to -4 over -3, b over a. 4 over 3, 1.33. And if you find it out, theta is going to be equal to 4.07. 4.07, so I have a 4.07. I'm going to get what? So this is going to be actually, I'm missing the 5 here. So I get 5 CIS 4.07. Okay? So that's it. So, it's kind of interesting that we can go and change this guy to look like that, all right? But what's the whole point in this? Why do we do this, okay? Why do we do this, okay? We'll show you the reason where this comes in very, very handy is when you do multiplication, or division of complex numbers. So if you remember correctly, if you go back and you think of how we did those before, let's say I had, -1 plus root 3i over, well, let's just do the one, okay, so if I have 2 plus 4i, if I want to divide this, how do I do that? Okay, if you remember correctly, way back when, we multiplied the top and bottom by the conjugates, right? Then I have to multiply this out, you have to multiply this guy out, divide them out, and it becomes very complicated or cumbersome, right? Whereas if you use the polar forms, what we are able to do is that if I have z1 is equal to a1 plus b1i, r1, and I do a cis theta 1, if I had a modulus of r1 and an argument of theta 1, and z2 is equal to a2, b2i, r2, cis theta 2. The interesting thing is that z1 times z2 becomes r1, r2, cis theta 1 plus theta 2. Very neatly. This becomes very smooth. In other words, you multiply the moduluses together and you just add the arguments and then you're done. Okay? Which is kind of cool for multiplication, but where it comes in really handy is when you divide, you get the same thing and becomes this. So this is where you really get to use and enjoy the power of the polar form, okay? And that is in page 505. There's a blue box there that shows you the operations of that. Okay? So let's see if we can actually use this. Let's see if we can actually do this. Let's go to example number 3. Let's see if we can do example number 3. Example number 3, use an algebraic method to Z1, Z2, where Z1 is 25 root 2, CIS, and the argument was negative pi over 4. Okay, Z2 is 14 pi over 3. And they want us to find the product. So they want the product. So it's going to be Z1 times Z2. It's nothing more than you multiply these two together. So I'm going to get root 250 times 7, 350. And then I'm going to get what? CIS negative pi over 4 plus pi over 3, which becomes 350 root 2 CIS. If I add these two together, I get that. That's it. See how simple that is? This is where we get to use the power of that theorem, okay? Example number 4. In example number 4, we have Z1 is 2 root 2, 135. So 2 root 2, and we have 135. And then we have 6 and 300. 6 and 300. And they want us to figure out the quotient, I'm assuming. Z1 over Z2, is that what we're asking? We are doing Z1 over Z2. Okay, so we're going to get the 2 root 2 divided by 6. This guy divided by this. Then I'm going to take the CIS, 135 minus 300. So I get what here? I get, this is 3, so I get root 2 over 3, CIS, 165. Okay? Well, it's negative 165. All right? If I do that, I'll just get a number. I'm not going to go through that. So there you go. So that's how that works. And so let's do one more thing. Let's go ahead and actually introduce de Moivre's theorem. So de Moivre's theorem, let's say that I have a Z is equal to R CIS theta. Okay, so what is Z times Z going to be? That's going to be this guy times that guy, so it's going to be R squared. And they're going to have CIS theta plus theta, right? Which is nothing more than what? This is going to be 2 theta, correct? CIS 2 theta. So let's say I want to do this one more time. What am I going to get? I'm going to get R cubed. And I'm going to get CIS times 3 theta. Okay? In other words, Z to the nth power is R to the nth power CIS n theta. And this right here is de Moivre's theorem, right? Okay, this is what de Moivre's theorem is. If you go to page 507, there's a blue box that shows that. Okay? So let's do example number 5. Let's do example number 5. Example number 5 says find I to the third using the Moivre theorem. So we're going to say example number 5. 1 plus root 3i, and they want the cubed of that, but they want us to do this using de Moivre's theorem. So we have to use this theorem. In other words, I have to change this guy. If I didn't use de Moivre's theorem, what am I going to end up doing here? I'm going to have to do this, right? And you can already see how cumbersome this is going to be if I do this, right? Okay, so we're going to use de Moivre's theorem. And in order to use de Moivre's theorem, I'm going to have to change this guy into the polar form that looks like this, right? So let's do that first. 1 plus root 3i. So the r is going to be what? R is going to be root of 1 squared plus that squared, right? Which is going to be equal to 2. Okay. So this is here is going to be equal to 2 1/2 plus like that, right? So now I have to find an angle where I have cosine is that and sine is that, okay? And if you think about that, that's going to be pi over 3. So you have 2 cis pi over 3, right? Okay. So now I want the cube. So this is going to be, the cube is going to be 2 cis pi over 3 cubed, which is going to be 2 cubed, right? This is going to be what? CIS pi, correct? So CIS pi, so this is going to be what? 2 cubed is 8. This is going to be the same as cosine pi plus I sine pi, right? This guy is 0, negative 8. See how simple that is? So that's how you use de Moivre's theorem, okay? Let's do one more. So let's do example number 6. Example number 6, they want us to find that using de Moivre's theorem. I get negative root 2 over 2 plus root 2 over 2i to the 8th. Okay, so I'm going to have to find the polar form of this guy first. So to find the polar form, I need to find the r. So r is going to be that squared plus that squared square root, which is 1. Oh, so this is actually a unit polar, right? Because this is the root, the r value is 1. Okay? So now I just need to find the argument, right? So the argument where cosine is negative, sine is positive. So cosine is negative, right? Sine is positive, so I'm over here. So it's obviously going to be here. So this is going to be 3 pi over 4. So I'm going to get, this is CIS 3 pi over 4. And now I want to go ahead and do that. So this is going to be nothing more than CIS, going to make 10, so it's going to be 3 pi over 4 times 8, which is CIS 6 pi, I guess, which is going to be equal to cosine 6 pi plus I sine 6 pi, right? This guy goes to 0. No, wait a minute. So, sine is 2 pi, so it's all the way right back here. So, this guy's going to, yeah, so this guy is 0, and this guy is 1. So, the answer should be 1. The answer is 1. Okay? All right, so that's how we do that. And we'll stop right here today.